The Pythagorean theorem is one of the most far-reaching results from the ancient Greeks. It is not only a cornerstone for the visualizable 2 or 3-dimensional Euclidean geometry, but also a guiding principle for the higher dimensional or more abstract setting in mathematics. As we proceed further into the foundation of geometry, we're going to see that the Pythagorean theorem is a characterization for the Euclidean geometry. In this video, we're going to look at 2 proofs of this important theorem. Let's review the statement of this theorem first. It says that if A and B are the lengths of the legs of a right triangle, and if C is the length of the hypotenuse, then A squared plus B squared is equal to C squared. In the first proof we present, we use similarity of triangles. For convenience, we denote the measure of the angle A as alpha, and the measure of angle B as beta. And we know that beta is equals to 90 degrees minus alpha. The trick is to draw the altitude on the hypotenuse. And we denote the foot as capital D. This altitude CD splits the triangle ABC into 2 triangles, ADC and DBC. We know that the angle ACD is of measure 90 degrees minus alpha, which is precisely beta. Similarly, the measure of the angle DCB is equal to 90 degrees minus beta, which in turn is just alpha. To sum up the observations, we have the following relations. For clarity, in this table, we put the angles in the same triangle into a same column, and we observe that the measure of the interior angles of these 3 triangles would either be 90 degrees, alpha, or beta, respectively. Consequently, we have the following similarity among triangles. Namely, the triangle CAB is similar to triangle DAC, which is also similar to the triangle DCB. I will suggest you to pay attention to the correspondence between the vertices of these triangles. It's important to keep this in mind when writing down the expression of the similarity relation. Upon the observation of the similarity relation among those 3 triangles, we can further exploit the properties of similar triangles. For convenience, let's denote the length of the segment AD as x, and the length of the segment DB as y. The similarity between the triangle CAB and the triangle DAC implies that the ratio between CA and DA equals the ratio between AB and AC. That is, B over X is equal to C over B. Similarly, since triangle CAB is similar to triangle DCB, we must have the ratio between BC and BD equals the ratio between AB and CB. Namely, A over Y is equal to C over A. To complete our proof, we just need to carry out some algebra. For instance, from the first relation, we have B squared equal to C times X, And from the second relation, we have a squared equals c times y. Therefore, the sum of a squared and b squared is just equal to c times x plus c times y, which in turn is equal to c times x plus y. However, the sum of x plus y is precisely the length of the side AB, which was denoted precisely by c. Therefore, we have the equality a squared plus b squared equal to just c squared, and that is the Pythagorean theorem that we are trying to prove. And we are done with the first proof. Now we move on to the second proof. In this proof, we will utilize the properties of congruent triangles and the properties of area. Suppose the triangle ABC is a right triangle with a right angle at the vertex C. The first move is to construct a square based on the hypotenuse AB. We denote the other two vertices of the square by D and E. Now, through the point E, we can draw a unique parallel line to the line AC. This line intersects the line CB at a point denoted by F. Similarly, through the point D, we can draw a unique line parallel to the line CB. And this line intersects the line EF at a point denoted by G, and it also intersects the line CA at a point denoted by H. Let's make a few observations. First of all, since the line CA is parallel to the line FE, and CB is perpendicular to the line CA, we conclude that CB is also perpendicular to FE. That is, we must have the angle BFE being a right angle. Secondly, if we denote the measure of the angle BAC as alpha and the measure of the angle CBA as beta, then beta is precisely 90 degrees minus alpha. On the other hand, by the construction, the quadrilateral ADEB is a square, so specifically, the angle EBA is of measure 90 degrees. Consequently, the angle FBE is going to be 180 degrees minus 90 degrees minus beta. But beta is equals to 90 degrees minus alpha, so this angle must be of measure alpha. Meanwhile, as two sides of a square, the length of BE must be the same as the length of AB. Therefore, triangle ABC must be congruent to triangle BEF by the angle-side criterion. With similar arguments, we can establish that the triangles at those four corners are all congruent to each other. As illustrated in the figure, know that the square based on AB at the center And those four right triangles at the corners form a larger square together. For convenience, we denote the area of the larger triangle as capital S, the area of the smaller square as lowercase s, and the area of the right triangle as r. Then capital S is equal to a plus b squared. Lowercase s is equals to c squared, and r is equals to 1/2 a times b. Clearly, the smaller square is just the larger square take away those four corners. Therefore, we must have the lowercase s equal to capital S minus 4r. When we carry out some algebra, we should have a squared plus 2ab plus b squared minus 2ab, which is just a squared plus b squared. Since the lowercase s is just c squared, we conclude that a squared plus b squared is precisely equal to c squared. By this, we complete our second proof of the Pythagorean theorem. Thank you for watching. I'll see you next time.